Hi, I'm Kian, and in this video I'm back with another question related to real analysis and calculus. And here our topic is continuity and differentiability. So we have a function here, f. We have also a g, but I'm not given that. I don't have that part of the function, but it's a piecewise function, f of x, which is basically equal to x sine of 1 over x for x is greater than 0 and is equal to x for x is less than or equal to 0. And we want to prove that it is continuous and then show that if it's differentiable or not. So first of all, what we can do is that to show continuity, there's a rule that we should know. For f of x to be a continuous at a point, then, or continuous in general, the limit as x approaches that value, as we say in this case, x will approach 0 of f of x should be equal to the function evaluated at that point, f of a, or in this case, f of 0. So what we can prove that basically here we don't have a single expression for our function. Here's a piecewise function. So we're broken into the left hand and right hand. So basically what we have to do is to take two different limits and see if they're equal. If both limits exist and are equal, then we can conclude that the limit as x approaches 0 of f of x exists. So for our left hand limits, let me change the color. I'm going to call it just LHL. So as x approaches 0, we can see that if we use a squeeze theorem, we can write this as sine of 1 over x over 1 over x. As x approaches 0 from the left, from the right, I'm sorry. So this would be, this would be right-hand limits. I'm going to just change it. This would be right-hand limits. As x approaches 0 from the right, so the x sine of 1 over x goes to 0 because of squeeze theorem. And the left-hand limit, which is for x is less than or equal to 0, as x approaches 0, x also approaches to 0. So we have concluded that the right and left-hand limits are equal. So that's a good thing because we know that this part is just 0. Because if the left-hand and the right-hand limit are equal, then the limit exists. Now for f of 0, what you have to do, you have to just plug in for in the function in which where we have a equal, a less than or equal or greater than or equal sign. So this is only kind of valued x sine of 1 over x when x greater than 0, but it's not including 0. But f of x is equal to x for x's that is less than or equal to 0. So 0 is also included. So for this, you have to basically plug in x, and if you plug in, we get just 0. So f of 0 is also 0. So we have shown that the limit as x approaches 0 of f of x equals the function evaluated at 0. And therefore, this function is continuous. Now, to show differentiability, I'm going to write really small here. We basically, it's very similar to limits. We basically have a left-hand side kind of derivative, a right-hand side derivative. If I'm going to write right-hand derivative as d. So if you take the derivative of this expression using the product rule, what we get is sine of 1 over x and then we get plus cosine, but derivative of 1 over x is negative 1 over x squared. So we get basically minus 1 over x times cosine of 1 over x. Now, when we want to evaluate this is not a limit again. This is a derivative at a specific point. When we evaluate this derivative at 0, we can see that this is technically not defined because we're taking sine of 1 over 0 minus 1 over 0. There's a lot of undefineds going here. So basically, the left-hand derivative really doesn't exist. It's undefined. But the right-hand derivative, you take a derivative is 1. The derivative will become 1, and therefore the left-hand and right-hand derivative, so the left-hand derivative is just 1, are not equal. So we can say that this function is continuous, but is not differentiable. Thanks for watching. I hope you enjoyed it, and goodbye.